Hello, and welcome to the Academy of Useless Ideas. Before we dive into today's topic, let's take a moment to ponder the nature of real numbers. They are like Platonic ideals, perfect and pristine, so elusive that we can only catch a fleeting glimpse of their true form. It's almost like trying to catch a unicorn in the wild. Take the infamous square root of 2, for instance. This irrational number is so unreasonably long that we could fill the entire universe with its decimal representation and still not come close to its true value. However, fear not, for we can use a sequence that converges to the square root of 2 to get a close enough approximation. The only problem is, when we start to operate with these numbers, how can we ensure that our operations respect this approximation? To further clarify this idea, let's consider two functions. The first one simply calculates the cube of a number, while the second one is equal to 0 for numbers smaller than the square root of 2 and equal to 1 otherwise. Now, since we can't calculate the square root of 2 exactly, we have to rely on an approximation to calculate these functions. Let xn be an increasing sequence that converges to a square root of 2. As we get closer and closer to the square root of 2, the value of the first function also gets closer and closer to its true value. However, in the second case, we don't get any closer to the true value of the function. So while the first function respects our approximation of the square root of 2, the second one does not. Now, how can we characterize functions that do respect our approximation? Now, this is where the concept of sequential continuity comes in handy. We say that a function from a metric space x to a metric space y is sequentially continuous at a point x in x if for every sequence xn that converges to x, the sequence fxn converges to fx. So, if f satisfies this condition for every point x in x, we say that f is sequentially continuous. In simpler terms, the idea is that we can push the limits inside the arguments of the function without affecting the limit of the function itself. Another way of characterizing a function that respects approximations is through the use of open balls. The idea here is that you can find a precision around x that leads to a desired precision around fx. We measure those precisions using balls around x and fx. More formally, we say that a function is continuous at x if for every ball by around fx, there exists a ball bx around x such that f of bx is completely contained in by. In other words, if you want a precision of fx given by by, you can achieve it by using a precision of bx. We can write the same definition using the radii of the balls, which leads to the standard epsilon delta definition of continuity at a point x. That is, f is continuous at x in x if for every epsilon greater than 0, there exists a delta greater than 0 such that for every x prime, that is delta close to x, f of x prime is epsilon close to fx. As before, we say that f is continuous if it is continuous at every point. In metric spaces, it can be proven that a function is continuous if and only if it is sequentially continuous. Therefore, in metric spaces, these definitions are interchangeable. However, the definition using balls can be extended to non-metric spaces where the two concepts can be slightly different. Let us now prove the equivalence of sequential continuity and continuity in metric spaces. For the forward direction, let's assume that f is continuous and that xn is a sequence converging to x. Our goal is to show that fx is the limit of the sequence fxn. To do so, consider an arbitrary open ball by around fx. Since f is continuous, we can find an open ball bx around x such that f of bx is contained in by. Since xn converges to x, we know that all but finitely many elements of the sequence lie in bx. This means that all but finitely many elements of the sequence f of xn lie inside by, which implies that the sequence f of xn converges to fx. For the other direction, let's assume that f is not continuous. Therefore, there exists an open ball By around fx such that for every open ball Bx around x, f of Bx is not contained in By. In particular, for every natural number n, we can choose xn that belongs to the ball of radius 1 over n around x, but such that f of xn is not in By. Under this construction, the sequence xn will converge to x, but the sequence f of xn cannot converge to fx because none of its elements lie in By. The relationship between sequences and open balls suggests that we can define limits of functions in the following way. We say that a limit of fx prime as x prime approaches x exists if there exists a y in y such that for every ball By around y, there exists a ball Bx around x such that Bx minus x is completely contained in By. The reason to exclude x from the ball is so we can make sure that we are approximating x without including it in the set of values we are considering. Additionally, by excluding x, we can define the limit even when the function is not defined at a point. For example, the function sin x over x is not defined at 0, but we can still calculate the limit as x approaches 0. This limit tells us that if we wanted to continuously extend sin x over x, we would want to give it the value of 1 at 0.